Do you work on defect detection or quality control? These use cases have a common goal: classify objects in images. What we need is to detect the object in an image and to classify the object. For example, let's say that our task is to classify the dice. We need first to detect the dice and then to classify which number it is. We want a solution that, when given a new image, will tell us what is the number on each die. In this tutorial we will focus on the first part of the task, to detect objects in an image. Instead of hand-tweaking the solution with different image processing tools, we train it from examples, using statistical pattern recognition. In general, these are the steps needed. We need to choose what local image information to use, we prepare training dataset, we build a local image classifier, and we define the objects with segmentation. Let's see how we can do it in our dice example. The dice objects and background differ in their color. Therefore, we will learn from the RGB color of individual pixels. If our object or background contains strong texture or edge information, we may represent small image neighborhoods like we did in previous tutorial. Our goal is to distinguish between dice and background. We paint dice and background labels. We save the labeled image back to MATLAB workspace into the variable A, and we repeat the procedure for a second image, in order to have a more general training set. We then put together the training set. This is the scatter plot of C, the combined set. It is a 3D space with the RGB values as features. We can still visualize the data as an image, by selecting the subset of data using the image label. We are interested in the dice class, so we train a detector for it. We use a Gaussian model. We also specify the name of the non-target decision, to avoid that STDetect uses non-dice. It is useful to visualize the detector behavior on the image A. From the ROC curve, we can observe that our classes are separable. Note that it is still useful to adopt statistical model and ROC analysis as we fix the operating trade-off to avoid gaps in the objects. Instead, we rather live with some false positive in the background. By pressing the S key, we can save the ROC operating point back into the PD detector pipeline. We now apply the classifier to our image. This is the result. All pixels are labeled as background or dice. We can now segment the separate objects present in the image based on the classifier decisions. This step generates a new label set, called object. We save the entire dataset to MATLAB workspace. The data A has multiple labels: a class label, which is set by default as unknown, an image label that stores the file name of the original image, the decisions of the dice detector, which label each pixel into dice or background, and then the object label, that groups under the same object all connected pixels that have the same decision label. For the dice and background class separately, as the segment will label as one unique object all connected pixels. For example, we can see that 947 pixels form the unique object called diceObject31. Objects smaller than 500 pixels are merged into one class called smallObjects. We can repeat the same procedure for a new image by scripting. Summarizing, we have shown how to detect objects in an image using a classifier trained on local information and the segmentation of the classifier decision labels. Thank you for your attention.